Assalamualaikum warahmatullahi wabarakatuh. My name is Ainul Hasbi binti Azrin Masidi, and I will talk about introduction. What is Profenofos? Profenofos is an organophosphate insecticide widely used in agriculture to control pests on various crops, including cotton, maize, and vegetables. Developed in the 1970s, it is known for its effectiveness against a broad spectrum of insects. However, its usage has raised concerns due to its potential adverse effects on human health and the environment. Profenofos inhibits acetylcholinesterase, an enzyme essential for nerve function, leading to neurotoxicity in humans and wildlife. Chemical structure. The chemical structure for profenofos is an organophosphate compound. Its structure includes a phosphorus atom bonded to an oxygen phosphorothioate with additional groups including a bromine substituted phenyl ring, an ethoxy group, and a propyl thio group. Properties of profenofos. The appearance of profenofos is yellow to amber liquid. The solubility is it is lightly soluble in water, highly soluble in organic solvents like acetone and benzene. The boiling point is it decomposes before boiling. The stability is it is stable under normal conditions but decomposes under extreme heat and light. Common uses in agriculture. Profenofos is widely used as an insecticide and acaricide in agriculture. It is primarily utilized to control a variety of pests, including first, insects, such as cotton bollworms, aphids, thrips, armyworms, and whiteflies. Second is crops, extensively applied to cotton, vegetables, such as cabbage, potatoes, tomatoes, and tobacco. It acts by inhibiting the enzyme acetylcholinesterase, which is essential for the proper functioning of the nervous system in insects, leading to their paralysis and death. Potential health risks associated with profenofos residue in food. Exposure to profenofos residues in food can pose several health risks to humans. First is acute toxicity. Symptoms can include headache, dizziness, nausea, vomiting, abdominal cramps, sweating, blurred vision, and muscle twitching. High levels of exposure may lead to respiratory distress, convulsions, and even death due to respiratory failure. Second is chronic toxicity. Long term exposure can cause neurological effects such as memory impairment, depression, confusion, and tremors, disruption, and reproductive. Regulatory standards. Many countries have set maximum residue limits for profenofos in food products to minimize health risks. Regular monitoring and adherence to these standards are essential to ensure consumer safety. Environmental impact. The extensive application of profenofos has led to its persistence in the environment, particularly in soil and water. It can leak into water bodies, affecting aquatic life, and can accumulate in the food chain, posing risk to human health through contaminated food products. Residual levels in crops like oranges can be particularly concerning as these are directly consumed.
Next, for sampling method. First, selection of sampling site. For high consumer traffic, choose market with a high volume of fresh orange juice sales to ensure the samples are representative. Geographical distribution. Include markets from different regions to account for potential variability in Profenofos level due to the local agricultural practice. Next, sample size. Statistical relevance. Collect a sufficient number of samples to ensure the results are statistically significant. Typically, 20 to 30 samples are recommended to provide a comprehensive analysis. Vendor diversity. Sample from a variety of vendors within each market to capture potential differences in pesticide residue due to different supply sources. Collection protocol. Standardized containers. Use sterilized amber glass bottles for sample collection. Amber glass helps protect the juice from light, which can degrade certain compounds. Purchase samples. Buy fresh orange juice directly from vendors as sold to a customer. Volume. Aim to collect at least 250 ml of juice per sample to ensure there is enough for multiple analysis and potential repeat testing. Immediate sealing. After collecting the juice, seal the bottles immediately to prevent contamination and degradation. Record keeping. Maintain the detailed log of each sample, such as date and time, location, and storage condition. Next, storage and transport. Temperature control. Store samples in a cool condition, ideally at 4 Celsius. Use portable cooler with ice pack for immediate transport to the laboratory. Avoid contamination. Ensure bottles remain sealed and are handled with clean gloves to avoid introducing contaminant. Timely transport. Transport samples to the laboratory as quickly as possible, ideally within 24 hours of collection, to maintain sample integrity and minimize degradation. Lastly, laboratory handling. Reception and logging. Upon arrival at the lab, log in the samples, noting the condition and storage temperature. Preparation for analysis. Prior to analysis, bring sample to room temperature and homogenize them if necessary to ensure consistent result.
For extraction method, the appropriate extraction method we choose quenchers because it stands for quick, easy, cheap, effective, rough and safe method. Is highly suitable due to its efficiency and applicability for fruit juice matrices. Solvent extraction techniques are designed to achieve maximum analyte yield from the base matrix. Analytes of interest are extracted from the sample matrix using water-miscible solvents, usually acetonitrile, and high concentration of salt and or buffering agents. Advantages for this method is sample preparation, uses fewer solvents, and provide high recovery rates for a wide range of pesticide. And for disadvantages, it might require further clean steps for complex matrices. Quenchers method, it provides any step. For the first one is sample preparation, which is the sample orange juice is collected and homogenized to ensure a representative sample. Then extraction. A portion of homogenized sample is taken and mixed with an appropriate solvent, often acetonitrile, to extract the target analyte from the matrix. Then is cleanup, which is the extract is subjected to cleanup to remove interfering matrix components such as pigment, fat, and sugars, which is could interferes with analytical instruments. Is concentration. After cleanup, the extract is typically concentrated to reduce the volume, making it more amenable to analysis. Concentration can be achieved using techniques such as evaporation under gentle nitrogen flow or solvent exchange. Then for analysis step, the concentrated extract is then analyzed using chromatographic techniques such as gas chromatography (GC) or liquid chromatography (LC), often coupled with mass spectrometry (MS) for detection and quantification of target analytes. The Quenchers method offers several advantages, including simplicity, speed, cost effectiveness, and effectiveness in removing matrix interference. It has become the method of choice for many laboratories involved in pesticide residue analysis in food and environmental samples due to its robustness, and reliability. Additionally, it has been extended to the analysis to other classes of compound beyond pesticide, making it a versatile samples preparation technique in analytical chemistry. Comparison for two methods, which is solid phase extraction (SPE) and liquid liquid extraction (LLE). For the first one, we compare about selectivity because SPE is the selectivity of SPE can be controlled by choosing a specific sorbent material that interact selectivity with the target analyte, which is another one, well, which is LLE. The selectivity of LLE depends on the choice of solvent pair and the portion and partition coefficient of the analytes between the two pieces. Then sample volume for SPE suitable for processing smaller sample volume, typically in the range of milliliters, which is LLE suitable for processing larger sample volumes, often in the range of tens of hundreds of milliliters. Then solvent usage of SPE generally requires less solvent compared to LLE since only the elution step involves a significant volume of solvent. LLE is typically requires larger volumes of solvent for extraction and subsequent washing steps. Then metric effect of SPE can be less susceptible to metric effects since the solid phase selectivity retains the target analyte. When LLE is metric effects may be more pronounced due to potential for co-extraction of matrix components into the organic phase. And for the lastly is application. SPE widely used in environmental, pharmaceutical, and food analysis, particularly for trace level analysis and sample cleanup. For LLE is commonly used in sample preparation for liquid chromatography (LC) and gas chromatography (GC), as well as in industry such as pharmaceutical and petrochemicals.
Here is analytical instrumentation. The selection of analytical instrument. For the analysis of Profenofos in fresh orange juice, the choice of analytical instrumentation is crucial to ensure accurate, sensitive, and specific detection given the properties of Profenofos and the metric involved orange juice. Gas chromatography coupled with mass spectrometry (GCMS) is selected. Why we choose GCMS? First, I want to explain about the principle and functionality of gas chromatography, where this method separates volatile compounds based on their interaction with a stationary phase and a mobile phase. These compounds are separated by their boiling points and interactions with the column material as they travel through the column. And for the mass spectrometry, after separation by GC, compounds are ionized, fragmented, and detected in the mass spectrometer based on their mass to charge ratios. This provides a unique spectral fingerprint for each compound, allowing precise identification and quantification. Why GCMS Part 2? This is advantages of GCMS. First advantage of GCMS is high sensitivity and specificity, where GCMS can detect very low concentration of Profenofos, making it suitable for analyzing complex samples like orange juice. And the second one is accurate quantification. In the mass spectrometer, accurately measures the amount of separate compounds and crucial for determining Profenofos level. And the last advantages of GCMS is identification, where the mass spectrometer provides detailed structural information, allowing for the identification of Profenofos even among other substances. Next, the comparison GCMS with other analytical instruments. First, we talk about the high-performance liquid chromatography HPLC. The recovery rates for HPLC can achieve good recovery rates for a wide range of compounds, including pesticides. However, Profenofos, being an organophosphate, is better suited for analysis by GC due to its volatility. Then, under separation efficiency, HPLC provide high separation efficiency but may require derivatization for certain compounds to enhance detection. And for their sensitivity, HPLC is sensitive, but GCMS typically offers greater sensitivity for volatile organic compounds. And the next analytical instrument is liquid chromatography coupled with tandem mass spectrometry, or we call LCMS, MS. And their recovery rate is LCMS, where MS provides excellent recovery rates and sensitivity, especially for non-volatile and thermally labeled compounds. And their separation efficiency, LCMS offers very high separation efficiency and is suitable for complex mixtures. Then the sensitivity, LCMS is highly sensitive and capable of detecting multiple residues in a single run. However, GCMS is generally preferred for a volatile and semi-volatile compound like Profenofos due to its superior separation and identification capabilities. And the last analytical instrument is solid phase microextraction, SPME. Their recovery rate, SPME is an extraction technique that can be combined with GCMS for efficient analysis of volatile compound, offering high recovery rates with minimal sample preparation. Then, for their separation efficiency, when combined with GCMS, SPME provide excellent separation and detection of volatile compounds like Profenofos. And the sensitivity is SPME, GCMS is highly sensitive and suitable for detecting trace level of pesticides in various metrics.
In conclusion, the quenchers, which are quick, easy, cheap, effective, rugged, and safe method, when paired with GCMS analysis, is an excellent way to identify and quantify Profenofos in fresh orange juice. GCMS, with its excellent recovery rates and separation efficiency, is appropriate for this application. The presence of Profenofos in orange juice samples from night markets indicates potential health risks for consumers, emphasizing the needs for regular monitoring and strong regulatory controls. These are recommendation action for consumers, vendors, and regulatory bodies. For consumers should inquire about pesticide use or look into alternatives. Consumers can reduce their exposure to pesticide residue, such as buying organic because they are grown without synthetic pesticide, and truly wash fruits and vegetables under running water to remove surface residue. For vendors should prioritize acquiring fruits from trustworthy suppliers and ensure adherence to food safety guidelines. Regular pesticide residue testing and transparent labeling can help to create consumer trust while also protecting public health. For regulatory bodies should establish stricter monitoring in food products, enforce vendor compliance with safety standards, and educate the public about the risks connected with pesticide exposure. Furthermore, working with agricultural authorities to encourage sustainable and safe farming techniques can help reduce the usage of harmful pesticides.